We defined transmutation the other day as the conversion of one element to the other. We said radioactivity is one way in which transmutation can occur, a mechanism in which transmutation can occur. We're going to learn two more mechanisms today in which transmutation can occur. The first one is called nuclear fission, and the second one is called nuclear fusion. If you've taken biology class, you probably remember talking about mitosis, cellular mitosis. Okay, what is mitosis? Doesn't seem to have anything to do with this, right? But I'll make that tie in just a second here. What's mitosis? Yeah, it's when one cell splits into two. Sometimes we hear mitosis referred to as cellular fission. You guys ever heard that term, cellular fission? Yes? Some of you have, some of you haven't. Cellular fission, cellular mitosis, cellular fission is when one cell splits into two. Nuclear fission is when one nucleus that's heavy splits into two lighter nucleus or nuclei. I've got an example printed on the board here right now. This is not the only example that you could see by any stretch of the imagination. But in this example, you can clearly see that one heavy nucleus, uranium-235, splits into two lighter nuclei, krypton-92 and barium-141. There's also some neutrons in the mix here, and there's some energy in the mix as well. We're not going to pay any attention to those when we're determining what kind of reaction it is. They're important. They're really important. But they're not important for determining what kind of reaction we have. If one heavy nucleus produces two lighter nuclei, this is nuclear fission. Now, in order to make nuclear fission happen, and we can make it happen, we force it to happen all the time, unlike regular radioactivity. What we do is fire a neutron at the uranium-235. Uranium-235 is radioactive. It will eventually decay on its own, producing an alpha particle decaying into thorium-231. But it may take a long, long time. We can make it happen quicker, change the reaction a little bit, make it happen quicker by firing a neutron at that uranium-235. It's kind of analogous to, we've got a chunk of ice. Okay, we want to break apart that chunk of ice. It's crackling. We hear it ready to go. We think it's going to break apart, but it's just not going. So what do? We take a hammer to it. We hit it with a hammer, and we cause that chunk of ice to break apart now. So it was radioactive. It was ready to do something, or at least it seemed like it was ready to do something, but we kind of kick-started it into doing it. The neutron is the hammer. The uranium-235 would be the block of ice. Now, the actual mechanism by which this happens is not a hammer blow to a piece of ice. The neutron actually gets absorbed by the uranium-235 for a brief moment in time, becomes uranium-236, and then turns around and decays into krypton and barium. But if you take a look at the numbers here, the mass number on the left-hand side, 236, the atomic number 92. On this side, we have 233 and 92. We're missing something on the right-hand side. Not missing any protons because we still got 92 of them. What are we missing? Looks like we're missing some neutrons. In fact, we're missing 3 of them. Add those 3 neutrons in there, and we end up getting 236 on the right-hand side, which is exactly what we want to make sure that the law of conservation of charge and the conservation of nucleon law applies. Now, you also get some energy released. That energy released is actually comes from matter, mass, being converted to energy. And that's a little bit weird, right? We talked about that a little bit when we talked about the Compton effect. Matter and energy are 2 different forms of the same thing. When you look at the mass of what we start with here, the parent nucleus, and the mass of the daughter nuclei, the mass of the daughter is less. We lose mass. It disappears. It's converted to energy. This energy, by the way, in a single nuclear fission reaction is about enough energy to move a speck of dust. That's it. That's it. So it's not nearly as powerful as we might think that it is. A single reaction might generate enough energy to move a speck of dust. Now, you compare that to a chemical reaction, and it's way more than a single chemical reaction, right? A single chemical reaction would never generate enough energy to move a speck of dust. Take a lot more chemical reactions than a single reaction to do that. But still, it's not nearly as powerful as we might think. So, if it's not as powerful as we might think, if this reaction will move a speck of dust, then how do we power a city with this, with a nuclear power plant? Or how do we blow up a city, as in the case of the Americans bombing Hiroshima in 1945? If we move a speck of dust with one reaction, then we must need a whole lot of reactions, right? We need this reaction to grow exponentially and continue on so that we get an exponential number of specks of dust being moved. How does that happen? What happens to a process called chain reaction? Chain reaction was when the products of one reaction cause more reactions. We have a neutron being absorbed by uranium-235, becomes uranium-236, splits up, but it produces 3 more neutrons. Those 3 more neutrons could cause 3 more reactions as they get absorbed by 3 more uranium-235s. Now, those 3 more reactions would produce 9 neutrons now. Those 9 neutrons would produce 9 more reactions, which would produce 27 more neutrons, which would produce 27 more reactions, which would produce 81 more neutrons, and so on, and so on, and so on. This could conceivably grow so quickly that within a small fraction of a second, we have enough specks of dust being moved that a city can blow up, or a city can be powered by electricity. You know that when the Americans dropped the bomb on Hiroshima in 1945, first of all, the bomb on Hiroshima was a uranium bomb. The bomb on Nagasaki was a plutonium bomb. Do you know why they didn't use uranium the second time around on Nagasaki? Because they ran out of gas. They ran out of fuel. Uranium-235 is an uncommon isotope of uranium, but it's necessary for this reaction to take place. Something like 98% of naturally occurring uranium is actually uranium-238. And it's difficult to separate uranium-235 from 238. They've got to do that if they want this to work, but it's difficult. They have to go through a process called enrichment. Enriching uranium-238 to uranium-235 is challenging because chemically, uranium-238 is identical to uranium-235. You can't separate them using some kind of chemical reaction. You've got to use some kind of physical means to do that. And what they typically would do is use something called a centrifuge, spin it around. Things that are heavier go to the outside, kind of like a blood centrifuge, right? Separate plasma from blood and components from blood. Except it's a little bit harder to do with uranium than it is with blood. We separate it so that we purify the uranium. We get this itty little bit of uranium-235 out of the uranium-238 and pile it off over here and save it up until we have enough to make a bomb. It took about 3 years for the Americans to get enough uranium-235 out of this to build a single bomb. In fact, that bomb was never even tested. The one they dropped on Hiroshima, they just trusted that it would work. They never tested it because they didn't have enough fuel. They didn't have enough uranium to make 2 of them. They had enough to make 1. They just trusted that it would work. When they dropped that bomb, they dropped about 50 kilograms of uranium. That was the weight of the uranium that was used to blow up Hiroshima. 50 kilograms. Okay, sounds like a lot. It doesn't sound like all that much, actually, when you think about enough to blow up a city, right? Here's what's even more interesting about the whole deal. The amount of uranium that actually exploded was less than 5 kilograms. More than 45 kilograms never even exploded. Why? Because this grows so quickly. This chain reaction happens so quickly that the bomb actually blew itself apart before the remaining 45 kilograms could explode. The uranium in the remaining 45 kilograms, the nuclei were so far away from each other because of the explosion that these neutrons couldn't get absorbed by the uranium and continue it on. Imagine, less than 5 kilograms blew up a city and killed over 100,000 people. Imagine if 50 kilograms had exploded. Now, having said that, American scientists knew that would happen. They expected that. They didn't know exactly how much would explode, but they knew that it wouldn't all blow up because they knew that the bomb would blow itself up before it had a chance to explode the rest of the uranium. All right, that's nuclear fission. The other kind of transmutation reaction that we're going to talk about today is called nuclear fusion. This is when we fuse two nuclei together. It's when two light nuclei become one heavier nucleus. This is only one example. Notice in this example, we've got H2 and H2. This is a heavier version of hydrogen, a heavy isotope of hydrogen, combining with another heavy isotope of hydrogen, producing helium-3. This is not an alpha particle. Helium-4 is an alpha particle. Chemically, it's the same, okay, but nuclearly, I don't know if that's a word or not, it's not the same. Different properties of the nucleus because one less neutron. It also produces a neutron right here, and it produces some energy. The energy released, listen very carefully to what I'm about to say, a couple different sentences here. The energy released in a single nuclear fusion reaction is less than the energy released in a single nuclear fission reaction. The energy released in this reaction is less than this. We think of fusion as being this huge source of energy, right? The Americans developed a fusion bomb, the H-bomb, in 1952. Way more powerful than the bomb that was dropped on Hiroshima. But yet I'm telling you right now that the energy that's released in this reaction is less than the energy released in this reaction? Yeah, I am. But listen carefully to my next sentence. The energy released per kilogram of material in this one is way more than the energy released per kilogram over here. Look at the mass of this. Uranium-235, we have, in a neutron, we have 236 protons and neutrons. Here we have 4 protons and neutrons. Of course, this reaction will release less energy because you start off with so much less fuel in a single reaction. But if you take 50 kilograms of this, which is what the Americans did, versus 50 kilograms of this, 50 kilograms of this will give you way more energy. A single reaction won't, but per kilogram, fusion releases way more energy than fission does. One reaction, fission wins. Per kilogram of fuel, fusion wins by a long shot. Now, how does this one continue to go? Because the neutrons don't have anything to do with making it happen. It's actually the energy. This is tough to make happen. And the reason is because we have to pump energy into this to kickstart it. The reason we have to do that is because hydrogen nuclei, any nucleus, is positively charged. When these two positively charged nucleus get close together, they repel each other. And the closer they get, the more they repel. Remember Coulomb's law? As R goes down, F goes up. The force of repulsion gets ridiculously high here. We have to overcome that somehow, that force of repulsion. We overcome it by supplying some energy to it, usually in the form of heat, although not always. That energy causes the positive nuclei to overcome the force of repulsion, fuse together, and release more energy than we started with. This is the reaction that takes place in the sun. Right? The sun has lots of hydrogen in it. It's actually different isotopes here. You got some H3, I think, in the sun. Same basic idea, though, right? How does the sun sustain it? Because the sun is hot. You've got so much heat in the sun, the sun has no problem causing the hydrogen nuclei to fuse together, producing helium, and then causing more energy, which goes in, some of which goes into causing more hydrogen to fuse together. Energy-wise, per kilogram, this produces a lot more energy. Energy-wise, per reaction, it produces less. One more thing that I want to use to distinguish now between these two reactions. One of the big issues with Hiroshima and Nagasaki was the explosion itself. One of the issues was the fallout from the explosion. In the decades that follow, people are getting cancer from radioactive fallout. Although the amount of cancers that are developed from the nuclear fallout left in Hiroshima and Nagasaki is not as much as we often tend to think. What we often do is look at the number of cancers that are in Hiroshima and Nagasaki and say, oh man, this many cancers caused by nuclear weapons. People get cancer. Sadly, people get cancer independent of nuclear bombs, right? If you subtract the number of cancers that we would expect to occur from the cancers that have occurred, it's not nearly as big as sometimes we're led to believe. Still, I'm not trying to minimize it, it's still serious, but it's not as big as we would be led to believe. Bottom line is, there is nuclear fallout. These products, krypton and barium and whatever other products come from other nuclear fission reactions, are highly radioactive. So this happens, and then after this happens, for the decades that follow, you get a bunch of alpha, beta, and gamma decay. So the explosion is bad news, but the next 50, 60, 100 years are bad news as well. The one thing about this, nuclear fusion, although the energy per kilogram released is much, much more, the product that we get is, for the most part, safe. Okay? It's a much safer, not radioactive element that's produced there. So it's, for the most part, harmless. We'll say it's relatively harmless. Given the same amount of mass, you get a much bigger explosion, but you don't have the radioactive fallout. Right now, we generate electricity by using nuclear fission. It produces radioactive material that we've got to deal with. And usually we end up burying it deep in the ground, pouring concrete over top of it and leaving it for future generations. Sounds bad, but in the end, at least there's no greenhouse gases coming off of it. So it's got that positive at least, right? We can't generate power right now by nuclear fusion, at least not on a practical level. When the time comes, and it probably will come, that we're able to generate electricity using nuclear fusion, this is a huge, huge deal. One, because it produces so much energy. And two, because, talk about clean energy, this is clean energy, right? We don't have any greenhouse gases produced, nor do we have these radioactive particles produced. You generate a ton of electricity and you got nothing bad coming out of it.